Hello, everyone. My name is Stephen Wang, and I'll be presenting the Traveling Salesman and Genetic Algorithms for Workshop 3 CSC 575 Algorithm and Complexity. The paper I'll be presenting is titled Solving NP-Complete Problems Using Genetic Algorithms. I have the citation here below, and I have a description of the credentials for the paper. So let's get started with a brief outline to make sure I cover my bases. I'll be explaining a clear description of the problem. I'll also provide a clear visual example of an input and the correct output for that input regarding this problem. I will explain a non-trivial algorithm for solving the problem that is not an exponential or factorial time brute force algorithm. We will be working with an approximation algorithm today. Finally, I will explain any analysis provided by the authors, such as time, space complexity, correctness proof, or experimental results. So let's get started with the problem itself. The problem is called the Traveling Salesman. And simply put, given a list of cities and the distances between each pair of cities, what is the shortest route to visit each city exactly once and return to the origin city? So from this diagram on the left here, you can see that we have 4 cities, and these are all the possible paths between them. What permutation of paths would allow us to visit each city exactly once, return to the origin city, and also be the shortest route possible? So possible inputs could be 1, 2, 3, 4, or it could be 1, 3, 2, 4, or it could be any combination of those 4 cities. The point is, you got to go from a starting city through all of the cities at least once, or once, and then return back to the origin city. This is an example of a distance matrix used by the author for their algorithm. And the way to read this is J is going to be your starting city and I is going to be your destination city. So say, for example, you're starting at city 1 or J equals 0. If you wanted to go to the second city or I equals 1, then that would take 17 miles. If you wanted to go from the first city to the third city, that would be 0 to 19 miles. Let's say you wanted to go from the third city to the sixth city. So it would be J equals 2 to I equals 5 for the third and sixth city, and that would be a distance of 6 miles. And so this is a reference table used by the computer during its algorithm to determine what the distance between 2 destinations are to calculate the overall path length. Using this example distance matrix, I have an example input here. We just follow the naming convention where we go from 1 to 6 because we need to visit every city 1 through 6. So you go 1, 2, 3, 4, 5, 6, as you can see here, and adding up the distance between each one of these points, your total distance traveled is 71 miles. So your input is going to be the path array or the order of destinations, and then your output is going to be the total distance traveled. Another example here is 135246. And this one's going to be, it's going to have a different output. It looks a bit more complicated, but it isn't actually all that much more distance. So it's important to check, and in order to find the optimal solution, it would require us to go through an exhaustive search method or brute force. The traveling salesman problem is NP complete, and so rather than going through the exhaustive search method, they would rather do an approximation algorithm. This is because the possible path set is enormous. In a symmetric traveling salesman problem, where the distance between 2 cities is always equal both ways, so city 1 to 2 is equal to 2 to 1, the possible paths available to you is negative n minus 1 factorial divided by 2. But this problem can devolve very quickly or get more complicated if you introduce asymmetric traveling salesman, where the distance between the 2 points are not equal going both ways. This can happen with one-way streets or differences between highways, depending on distance. In the real world, very rarely is it exactly equal. So then you have a possible path set of n minus 1 factorial. And of course, that gets increasingly more complex based on the number of cities you have available. So the paper tries to compare the exhaustive search method or brute force method, where you find every solution, find every distance, compare them for the best answer, to an approximation algorithm called genetic algorithm. Genetic algorithm assumes that solutions are chromosomes and its parts are genes. So the entire array is considered a chromosome, and each individual cell within that array is considered a gene or a part of that chromosome. And it goes through a process very similar to natural evolution in biology, where you have a selection stage where you have your first initial randomly selected population of solutions. You select based on fitness. Then you have them mate or crossover genes in order to create new solutions that are similar in fitness, but ideally slightly different in order to find a better fitness value. And then you also have a mutation operator in order to introduce additional variability or cast a wider net on what's possible to apply to the problem. And then you end with a new generation that is ideally more fit than the previous one. Same as evolution in nature. So we'll go through each stage. Selection, or the process in which we choose who to mate. Each chromosome in a generation or each solution is given a fitness score based on the result. So in this instance, in the traveling salesman, that would be the distance traveled. Selection, there are two primary methods. One is rank and one is roulette. So rank solutions, they rank the solutions from a generation by fitness and assign probabilities of those ranks. So for example, if I wanted to make a generation have 20 solutions, I could assign first place as 50% being chosen, second place being 30% being chosen, third place being 10% chosen, and then the rest is spread across whatever, the other 17 different places. So out of the next 20 or the following generation, and generations have to stay the same number in order to be reproducible, in order to continue. You don't whittle down to one. But in the next generation, 20 of them would be the first solution. Or you could do roulette, where you would have solutions selected proportional to their fitness. This does introduce some negatives. An example would be 3 solutions with a distance of 61, 1,000, and 2,000. This is an extreme example, but 99.99% of the next generation would be solution 6, 61, if those are the top 3 places, because every other answer is so far away from an ideal or a reasonable fitness score that the entire next generation would just be that, and then you would have a monoculture. You would have a lot of the same solution, which would not be good for your variability. You would not be able to search well. So those are some negatives for roulette. The two methods are rank and roulette. Crossover is when I take 2 solutions, I choose a crossover point. And at that point in solution, you swap the tails, or you swap these endpoints on the solution in order to create 2 different solutions. And this is in order to promote some level of variability and test different fitnesses in order to get to an ideally more fit answer. And then you can also have a mutation in order to add variability, where you can have random individual bits change. This is normally a very low probability, but you do that in order to prevent a monoculture. You want new things to pop up in order to test, in order to find the best approximate answer to your problem. And so applying genetic algorithms, the first test was to compare exhaustive search method, brute force, ESM to genetic algorithms. So what they did was they took different size distance matrices between 8, 9, 10, 11, 12 cities. They had a 20 solution population size initially for the genetic algorithm. And then they ran those 20 and produced 20 for each generation. They ran that 50 times or 50 generations. And the result is what you see here. Now, what's known about exhaustive search method or brute force is you're going to find the right answer or the best answer every time. So that way we can look at ESM result as the benchmark. Those are the absolute best answers for those distance matrices. But if you notice here with the exhaustive search method, it grows exponentially. First, it's 0.01 second, then 0.11 seconds, then 1 second, 12, and 135. It grows exponentially. Meanwhile, the genetic algorithm works on a time complexity of n. It's almost very linear. It's very close to linear in that regard. So based on the test results, when the number of cities is kept relatively small, the exhaustive search method algorithm works well in comparison because it always finds the best available solution and in a shorter amount of time than genetic algorithm. But increasing the size of the problem changes the outcome dramatically. You get from 10 to 12, you see an execution time of 100-fold. Meanwhile, you can still find an approximate or reasonable answer proportionally from genetic algorithms. So this seems to indicate that genetic algorithms is good for finding an approximate answer, at least for very large problems in a reasonable amount of time. You're going to save a lot of time using genetic algorithms. But test number 2 was to evaluate the lower and upper ranges of genetic algorithms for traveling salesmen. So how good can it get and how bad can it get? What they did was they did 100 executions of the previous test on each distance matrix for sizes 8 and 12. Same thing, population size of 20, 50 generations. And what they got was that the worst results can get significantly worse. And the best results will always be worse, of course. It's an approximate answer. What ends up happening if you average the two is that on any given genetic algorithm test, you can get up to 15 to 20% worse than the best solution found from the ESM algorithm. So you start to introduce some concepts of trade-off. Yes, you will always find a genetic algorithm answer that is approximately 15 to 20% worse in a fraction of the time, especially if you're talking about international or a national level with hundreds of cities and hundreds of towns. You're going to find a good answer or a 15 to 20% worse answer. But on that scale, can you really afford 15 to 20% worse? Is it worth your time to do 100 times the time to get it right? So that comes down to industry, that comes down to the individual decision. Genetic algorithms will always be an approximate algorithm. It will always find a close enough answer. It'll just take a lot less time. Next is to compare effectiveness between rank and roulette selection. So this test was to see which form of selection is going to be best used to approach the traveling salesman problem. And what they did was they took sizes 10, 50, and 100 for population size, and then tested the distances or the answer that they got between roulette wheel selection and rank selection. They found that roulette wheel selection works better. And the reason is this: the earlier example that I provided gave a huge disparity between fitness values. I gave 61, 2,000, 3,000, very crazy numbers, something like that. When you do that, you run the risk of having an enormous monoculture. But when all the fitness values are relatively close together, and in this instance, most of the answers are going to be relatively close together, you're going to have enough variability. And so it's hypothesized that these superior results are due to a relatively large population size and a relatively narrow spread of those fitness values. They note that all fitness function values were within a factor of 10 of one another. So in that specific instance, in this specific problem, it may be best to use a roulette wheel selection for the traveling salesman. But in conclusion, this paper demonstrates some of the positives and especially demonstrating the time complexity advantage of genetic algorithms versus a brute force method, but does acknowledge some of the weaknesses in terms of effectiveness or how approximate can it get to a correct answer with their genetic algorithm at this given point. And finally, they determined what would probably be the best way of doing selection for future trials. Thank you very much for listening to my presentation, and I hope you all have a good day. This has been my presentation on the traveling salesman and genetic algorithms.